Is the board clearly visible? No problem, right? So when there's a problem, let me know. So, and another important thing I want to remind you that chapter number 1 of the Shankar book, that is very important. If you want to go ahead in your present work, you have to uh, try to learn the first chapter of this book that we are following. Let us give some example. Let's discuss examples of a classical oscillator and a quantum oscillator, right? Classical oscillator and a quantum oscillator. Okay, so suppose we have a classical oscillator in the form of, you can say, a mass attached to a spring or pendulum or whatever. So we have a mass, for example, that is classical, right? Mass is equal to 2 gram, right? A body of mass 2 gram is having a frequency is equal to 1 radian per second, right? And let the amplitude of the oscillator is equal to 1 centimeter, right? So we want to estimate the energy of the oscillator. So an oscillator has a potential energy as well as kinetic energy. But if we are at one extreme of the positions, we are not at the in between positions. So suppose we are at the extreme position, one extreme or another extreme, then the total energy of the oscillator is of course potential. Right? So the total energy will then be equal to potential energy half m omega squared, and I will say x naught squared, where x naught is the amplitude of the oscillator. So that is equal to this 2, right? And 1 and 1. So it comes out to be 1 erg. Energy comes out to be 1 erg, right? And it is equal to 10 to the power minus 7 joules. So the total energy of a classical oscillator comes out to be of a normal classical oscillator in our everyday life, right? Suppose that it comes out to be 10 to the power minus 7 joule, right? Now, a quantum oscillator has a quantized energy, right? And we know that the energy of a quantum oscillator moves up or down in packets, right? And steps. And the one step is h cut omega. We can say that the two allowed energy levels of a quantum oscillator, they are h cut omega far apart. One level is away from its any nearest neighbor by an energy h cut omega. right? So we say that the quantum oscillator has quantized energy, right? Has quantized energy, right? And we say the energy of each packet that is equal to our each quantum energy of each quantum or each packet is equal to x squared omega. Right? We know that x squared 6 into 10 to the power minus 34 joules second. That is omega is how much? 1.
Excuse me, sir.
Yes.
Sir, that side is not visible.
That
Kindly,
is
if you
not
write
visible?
in. Yes, sir.
Okay, let me move it this. Is it
Ji,
okay now?
now it is clear, sir. Thank
Okay.
you.
So this comes out to be 10 to the power minus 27. We can say that the energy of a typical quantum oscillator is of the order of 10 to the power minus 27. The energy of a typical quantum oscillator is of the order of this number. A typical quantum oscillator, right? A normal quantum oscillator has this much energy. And in comparison with that, a classical oscillator has energy 1 hour. Right? This has energy 10 to the power minus this has 10 to the power minus 7 joule, 10 to the power are 1 hour, the energy of a classical oscillator, 1 hour, and the energy of a quantum oscillator 10 to the power minus 7 hour. Very, very small. Right? So now from here, we say the energy levels of the quantum oscillator are this much apart, right? We say if we have a quantum oscillator of this frequency, if we have a quantum oscillator of the same frequency, right? It has energy 10 to the power minus 27 erg. So this is 10 to the power minus 27 erg are around it, right? 10 to the power minus 34 joule, the energy, right? This energy, these breaks are very small is compared with this energy, right? So this classical oscillator, we can suppose that it contains, right? This contains about 10 to the power kind of 27 uh, energy levels, and it is practically not possible. We don't have any probe that can see this quantization in this because this number is very, very small. We cannot detect this thing in our classical oscillator. So therefore, this seems to be continuous, and this seems to be quantum are discrete. We get a discreteness in this, right? You know, I will give you a very rough example, right? very rough example of something that if you uh, if you look at it from a very far away point and you have a macro site or a panoramic view, things will look to you or you will see them continuous. For example, you have a flour, you know, grinding, wheat grinding as a machine which make you flour, or you have like suppose any grains you have. Suppose you have sugar. You know, you have big bags of sugar or this whole room full of sugar. And we know that sugar are small cubes. And if you make a small hole in this room at the bottom in a wall, then the whole sugar will fall onto the ground, right? But if we are looking at it from very outside, we will see a continuous flow. We will not see the graininess, the particle nature of sugar cubes. So this is kind of the same phenomenon. That is why it looks like continuous and this looks like quantized because we are at the micro level. This we will have another number. We can have a number to estimate if something will be like continuous, right? Or if something will be discrete or graininess will appear. So let us apply these results a little further and just get a parameter which we can use to estimate about the size of our system. If our system is classical and it is quantum, right? Okay. And we call that is the quantum number. So the quantum number of an oscillator, right? We know that the energy of an oscillator is equal to n plus 1 over 2 x squared omega, right? That is the energy of an oscillator. We know that, right? So we can say that is equal to n h cut omega plus half h cut omega, right? Okay. We can say E over h cut omega will be equal to n plus 1 over 2. We here know that n is equal to, right? 0, 1, 2, 3, and it is an integer. We know that it is an integer, right? So here we can get from here n is equal to E divided by h cut omega minus 1 over 2, right? Okay, so the energy of if E is equal to 1 erg, like classical oscillator, right? Classical oscillator. Oscillator, right? If we have a classical oscillator with energy 1 erg, then n will be equal to, right? And for our system, right, with the frequency omega is equal to 1 radian per second. So here we get n is equal to 1 divided by 10 to the power minus 27, if you remember. It was 1 erg the energy of the classical oscillator, and this graininess, this packedness, discreteness, one packet comes out to be 10 to the power minus 27. So n is equal to 10 to the power 27. So for a classical system, we see that n is equal to the quantum number 10 to the power 27. Right? If we have a quantum number for a system very, very high, the quantum number is very, very high, we can say that that is a classical system. And like the classical system will show continuity, right? So
Yes, sir.
the quantum number for oscillator is something that we can approximate the nature of a system. If the quantum number is very, very, very high, we will say that that is a classical system. And if the quantum number is kind of comparison to one or something, then we will say that is a quantum system. So there is a good parameter that helps us to know if a system is classical or uh, it is quantum. Okay. Uh, in our last lecture, right, we solved uh, the problem of harmonic oscillator. We found the energy, minimum energy, right? And we said that we can solve for the wave function of the oscillator. We did a very, very long procedure in that. It was a very long procedure, very tough mathematics, and so many arguments and so many suppositions, right? We found the energy, 0 point energy, minimum energy of an oscillator. Here, यहाँ पर आप uncertainty principle का एक करिश्मा देखेंगे, right? Let us see that how can we solve the problem of quantum oscillator, right? Or in shortcut manner. And we will use some trick, and we will use some logic and the energy minimization, and you will see that the problem of quantum oscillator will be solved in just a few steps, right? With the help of the uncertainty principle. So, uncertainty principle is a very useful principle. We will use the energy minimization. We will try to minimize the energy, right? And we will use the uncertainty principle, and we will solve the oscillator problem, right? Right? So, in the previous work, right, we said there is something called a 0 point energy. Even if a system is not oscillating, is not vibrating, there is zero temperature, there are zero phonons. We have a crystal, suppose, and they have at t is equal to zero, it will have zero phonons, no phonon present, right? Still, we will have zero phonon. So still we will have some energy. And we say that is the 0 point energy. That is not because of the vibrations, seems like. Similarly, if we have, an electromagnetic wave is an oscillator, right? There is an oscillator. So it's not because some field is oscillating, but there is some energy. If there are even no photons, still we will have a 0 point energy. For light or electromagnetic waves, no photons, but still we will have a 0 point energy, which will be equal to half h cut moment. Right? Okay. So we saw that we will apply the principle of energy minimization. We want to find the ground state energy. We want to find the minimum energy at t is equal to 0. The ground state energy or the minimum energy. Right? We want to find the ground state at t is equal to 0. You know what we did that? A minimum. Okay, if we have a classical oscillator, suppose we have a mass attached to a spring, right? And suppose it can oscillate in between these two positions. So when the energy will be a minimum, the energy of the oscillator will be a minimum if this mass m is at the center, x is equal to 0. Right? At the same time, if the kinetic energy equal to 0, it is resting at the center. If we have a pendulum, and that pendulum will have the energy will be minimum only, right? If it is at the mean position and if it is resting, which means the kinetic energy is equal to 0, which means momentum is equal to 0. So a state with x is equal to 0 and p is equal to 0. We will have the minimum energy. This oscillator will be in a minimum energy state, our classical oscillator. If it is at x is equal to 0 and at p is equal to 0. Right? So, what about the quantum oscillator? Here the situation should be the same. Right? Should be kind of the same. But there is a problem. If we say here in quantum oscillator, the energy is minimum again at x is equal to 0 and p is equal to 0, we are violating a very famous principle, and it's called the uncertainty principle. Right? We know x is equal to 0, definitely it's a state, and we know p is equal to 0. All both are completely determined. These are completely determined states, x is equal to 0 and p is equal to 0. And the uncertainty principle says that we cannot know both x and p with 100% certainty. So, therefore, in quantum mechanics, this state is not allowed. uncertainty principle, the uncertainty principle, right, does not allow a quantum state x is equal to 0 and p is equal to. Quantum mechanics does not allow a state which actually a kit state has x is equal to 0 and p is 0 because that will violate the uncertainty principle. Right? So if we cannot do this, so let us look for a state that is as close to this state as possible. We know that this is not an allowed state by the uncertainty principle. So we will try to be as close to as a minimum situation and a state with minimum energy, right? And if this state is, suppose the state is psi. Suppose we have a state psi which is as close to this state as possible, but not this state because this state is not allowed, right? So if we want to determine the energy uh, of the quantized oscillator, then we have to find out the expectation value of the Hamiltonian, right? The expectation value of the Hamiltonian. And the expectation value of the Hamiltonian with this state will be equal to psi h and psi. We write it like that, right? Now, what is the Hamiltonian, the expectation value of the Hamiltonian? The Hamiltonian is equal to like p squared divided by 2m, that's half m omega squared, and 2x squared. That is the oscillator energy, right? Here, only difference is that we will replace this with operators, p operators, momentum operators. P squared divided by 2m, the expectation value of the quantum harmonic oscillator. P squared divided by 2 equals half m omega squared nx squared. Remember, these are the p and x operators. Okay, if we look at quantum mechanics, if we try to minimize delta x from uncertainty principle, if we try to make our position certainty clear, right, and increase our position certainty, we get as close as possible to x is equal to 0. For a quantum oscillator, the uncertainty principle says that its momentum will get more and more spread. We will lose our information about its momentum. If we want to make certain our information about the position, then the momentum will become uncertain. So it means that if the particle gets to a precise position in the coordinate space and the configuration space, its position in the quantum space, its position in the momentum space spreads more and more and more. Right? There is a compromise when the product of delta P and delta X is the least. And if you remember that the function for which the product of delta x and delta p is the least, the minimum. It is the Gaussian function. Right? It is the famous Gaussian function. Okay, so to avoid the situation, let us analyze the problem a little further. Right? We are talking about the spread. If we try to become certain in momentum, we get a spread in position. If we try to become certain in, I don't know what did I say initially, but let me do it again. If we try to fix the position, to minimize the spread in position, the uncertainty in position, the spread in momentum gets more. Delta P increases. If we minimize delta P and try to know delta P precisely, we lose information about the spread in momentum, the uncertainty, the standard deviation. The deviation gets, so here is a problem of deviation in measurement, statistics. And you can learn the problem of deviation or standard deviation from Griffith in first few pages, like maybe 3 to 4 pages. He discusses the statistical nature of quantum mechanics, and he discusses the Griffith, the introduction to quantum mechanics. He discusses the standard deviation too, right? There he represented by sigma. Here, your book represented by delta p in momentum and the standard deviation in position as delta x. So, in standard, the square of the standard deviation, right? The square of the standard deviation in delta p square, right, is equal to p square average plus p average whole square. Right? Similarly, the spread, similarly, the spread in delta x, right, the standard deviation and position, square of the standard deviation position, that will be equal to square mean of the square, the square of the mean, right? Okay. Now we put these 2 and 3 right in equation number 1. We put them in equation number 1, right? So it's like we will get this p square because in equation number 1 we have p square average and x square average, and we want to get this value from here and this value from here and put it in equation number 1, right? So there will be, at the expectation value will be equal to delta p whole square, right? Plus p average square divided by 2 and plus half m omega square and to delta x whole square, right? Plus x mean whole square right? Now this is the Hamiltonian. This is the total energy of our oscillation. Right? Okay. Now here we can put, remember our method is energy minimization. We are trying to minimize energy. Why do we usually go after the energy minimization? It is kind of the law of increase of entropy. And people, systems are in equilibrium if they have maximum entropy, and systems are in equilibrium if they have the least energy. Right? So maximum entropy would mean minimum energy. So we are for the equilibrium of the system, right? We are going for minimum energy, and the energy minimization is a very strong tool in solving problems. So, uh, like we minimize the energy. So to minimize this Hamiltonian, which is the total energy, we can put P square is equal to X square is equal to 0. The uncertainty principle does not apply on it because they are just like numbers. These are mean numbers. They are not like the variables. No more variables. These are the mean just numbers, not the x and p variable. The uncertainty principle does not keep us from supposing this state. So we say, okay, to minimize the energy, let us put this equal to 0 and this equal to 0 at the same time, right? So what we get, H will be equal to delta P whole square over 2m plus half m half m omega square, right? And to delta x whole square, right? So here we have two variables, delta P, the spread in momentum, and the spread in position. Uncertainty in momentum, uncertainty in position. Let us bring the two variables to a single. And for this, we take help from the uncertainty principle. Right? In quantum mechanics, we know that delta x multiplied by delta p is always greater than r equal to h equal 2. We know that this is the uncertainty principle in quantum mechanics. It's a very famous principle, right? So this is the uncertainty principle. Here, I can take delta p greater than r equal to h equal 2 and one word delta x. Right? Okay. We want to put this thing, right? We want to put 5 into 4. 5 into 4. Okay, if we put 5 into 4, the mean value, let me erase this. If I put this thing into 4, I will get the expectation value of x is equal to, instead of that, I will write h cut, right, square, so it would be like p square, where p square, so it would be h cut square, right? And that 2 square will become 4, and 4 multiplied by 2 will become 8. So uh, there is 8. I am leaving this empty, not writing anything here. Right? Okay. 8 and delta x whole square. Right? I'm putting this thing into here. And since delta P is greater than this, therefore, this original thing, delta H, is greater than this thing. We have put a smaller thing, right? So I will say delta H is greater than R equals to, right? This thing plus R and omega square into delta X whole square. Right? Okay. So this is kind of inequality and equality, right? It's equal to it's also uh, the bigger. To get the smaller value of the Hamiltonian, the minimum value of the Hamiltonian, we differentiate this with respect to delta x squared and put it equal to 0. That is the calculus principle, right? To find the minimum or a maximum, we differentiate the variable, dependent variable, with respect to the independent variable. So let us differentiate this with respect to delta x squared and put it equal to 0, right? Hmm? Okay, before that, before going there, right, as I told you that the delta x delta p product, right, will be a minimum, right? This will be equal to h cut divided by 2. Delta x and delta p will be equal to h over 2 for a Gaussian function. So for a Gaussian, right, for h of a Gaussian function, if we consider psi to be a Gaussian, then h will be equal to, right, h cut divided by h into delta x2 plus 1 over 2 times omega square delta x whole. Right? Now we want to find the energy minimization. So we have a single variable. Here we have delta x and delta x. So we differentiate the Hamiltonian with respect to x to get the minimum energy, to get the ground state energy. Right? So we differentiate. It's Gaussian, right? With respect to delta x. We differentiate this with respect to delta x and put it equal to 0, right? To find the minimum Hamiltonian on the minimum total energy. When we do this, right, what we get is minus h cut divided by 8 and to delta x to the power 4 plus half m and omega square, and that is equal to, it's from here, h cross square, 8m delta x4 is equal to 1 over 2 and omega square. Right? Okay. H cut square over delta x to the power 4 will be equal to 4 m square omega square, or delta square from here. Right? Will be equal to h over 2 m omega. Delta x square is equal to that. Right? Now we found the value of delta x square. Right? So we can put it in. This is, take that one as 7 and this one is 8. Right? So if we put we put 8 into right? So we will put, this is the minimum. We said the Hamiltonian is a minimum now because we took the derivative of the Hamiltonian with respect to the delta x squared and put that equal to 0. So we say that according to calculus, that is the minimum, right? So the h minimum is now equal to, right? We put that, we will get h cut omega divided by 4 plus, if we put it here too, we will get h cut omega divided by 4. And that is equal to h cut omega divided by 2. So, the minimum energy of the quantum oscillator is equal to h cut omega divided by 2. And we found this in a very few steps. ठीक है, हमने यहाँ पर ज्यादा कुछ टाइम लिया, लेकिन हम स्लो जा रहे थे, हमने इसको ज्यादा थोड़ा सा स्लो किया, एक्सप्लेन किया. But actually, these are just a very few steps, right? The energy minimization, right? And then taking the differential of the Hamiltonian with respect to delta x square, applying the uncertainty relationship. Just applying the uncertainty relationship, we found the minimum energy. And we have supposed that, and we know that the uncertainty principle is a minimum for a Gaussian, and the Gaussian wave function, you know that. So the Gaussian wave function is a minimum, right? So time minimum, that is for the Gaussian. Right, and that is equal to m omega over 5 h cut to the power 1 over 4 and e to the power and omega x squared, right? Divided by 2 h cut. Okay. So found the minimum energy, that is negative, the minimum energy of the quantum oscillator. And we also got the minimum wave function, right? Minimum energy wave function. So that is the solution to the quantum harmonic oscillator with the help of the uncertainty principle, right? And we got also the energy, right? So we can now see that yes, this is the minimum and the ground state, they are the same, right? Just by reasoning. The minimum and the ground state are the same, right? This ground state, this minimum is the ground state. This minimum is the ground state, right? If we have any psi and we have psi minimum, right? And any psi, some psi, a state of the quantum oscillator. And this is the minimum, right? So the expectation value corresponding to this. So we have psi minimum and so the expectation value of the Hamiltonian with respect to this will be smaller than this, right? So you can say that psi minimum and h and again psi minimum, right? This will be less than or equal to the Hamiltonian with respect to this any function. Any function will have greater energy, right? So suppose that is right. If psi is supposed equal to psi naught, the ground state energy, that is our minimum. That is any state of the harmonic oscillator. But suppose we say psi is equal to psi naught. Suppose this state that we suppose that is the ground state energy. Then we can write this as psi minimum, the expectation value, right? That is less than or equal to, instead of this we write psi naught h into psi. And we know that this is the ground state wave function. Psi naught because we said that is the ground state wave function. We know that that is the energy at the ground state function. We call it the ground state energy. Sometimes we denote it with E0 or E naught, the ground state energy. Right? That is one situation. Okay, let us, we say, we want to prove something. If in your quantum, in your calculus and in your mathematics, we say, now let us do the converse. We do something from the one way and then we reverse. Right? So let us do the converse. And let us suppose now psi naught. If psi naught is the ground state, another reasoning. If psi naught is the ground state, then the Hamiltonian is psi naught. the ground state energy, and psi is any state. So that is the ground state, and psi is any state of the oscillator, quantum oscillator. Then this will be, of course, this Hamiltonian will be smaller than this. Right? If this is the ground state, we know the ground state energy is smaller than all the states. Now, if we suppose psi is lit equal to psi minimum, suppose let's say any of the state is psi minimum, then we will say psi naught and the psi naught is less than or equal to psi minimum and into psi minimum. Right? So compare equation number 11 and 12, 13, 11, 12, and 13. We see, look, this thing is less than this. Here, the psi minimum is less than or equal to this. Here, it is inverse, or upside down, you can see. Now we say here, this is less than or equal to this. So these two equations, they mean that actually they are equal to each other. So we said that psi naught and psi naught is equal to psi and psi. So that is the ground state energy. Our minimum energy, our E minimum, right, is the ground state energy. And the wave function is, the Gaussian wave function. It is the ground state wave function. Right? So this is how we use this is how we used to find. And then there was the final minimum was the Gaussian wave function. So in this way we used a few steps and the uncertainty principle and found in a shortcut way the 0-point energy of an oscillator and its wave function. 2. Let us do the. There is further. We will treat the quantum oscillator in energy basis. There are different bases. किसी बेस में कोई चीज किसी बेस में आसान होता है, कोई दूसरी चीज एक और बेसिस में आसान हो जाती है, right? So we solve some problems using spherical polar coordinates, and some problems can be used with or solved with rectangular coordinates, right? If you want to solve the problem of a particle moving in a circle, right, with the coordinate system is, or the basis is x and y, it will become very difficult for you. But if you want to change, if you change your basis to r and theta, to the polar coordinates, if you change your basis and treat the problem, and that r theta basis, the r theta system, then it will be a lot easier to solve a problem moving in a circle, a particle moving in a circle. Similarly, We can use different bases to solve quantum mechanical problems, right? So with the lectures that we did in class a few days ago, that was treating the quantum mechanical problem. It was in configurational basis, in X basis, X, Y, Z, right? Our coordinate system was the configuration space. Now we can treat the harmonic oscillator in energy basis, in which the coordinate system has energy axis, dimensions are energy, depends upon energy, right? So we will do that next time. See you. We will arrange another meeting then. Okay? I will inform you. Thank you for coming and joining me.
Thank you,
Are
sir.
there any questions? You let me know if you have questions.
So thank you so much.
Thank you. If there are any questions, let me know. If not, then goodbye to you and you leave
मेहरबानी
the
सर.
Mehrabani.
अल्लाह हाफिज सर.
Allah Hafiz. You can
सर
leave the
द बोर्ड सर लग टाइम की ब्लर होका ना
Ha.
नो आगा चिकम मुंग इनिशियल स्टेप्स कोल नो आगा टाइम बिया लग क्लियर नु सर बिया आखिर के उस क्लियर हो सर
Ha.
नो दा पके राजीज मे बी क्लास
Okay,
दौरान नेक्स्ट टाइम
you
बिया
know
मल तफ्ता
these things are in your book, so you will read your book too, and we will
सही
discuss. And I will see if I can upload this into YouTube, maybe or maybe not.
सही
Uh,
सही है सर.
so these
मेहरबानी.
things are present in the book, okay?
ओके
So
सर
you
थैंक यू
can
सो
always
मच.
remember, do not trust in my lectures.
ओके
Always compare these lectures with the book.
ओके सर.
And what is in the book that is correct and what I am saying here would be wrong,
सही.
right?
ओके
So
सर थैंक यू.
compare this always with the book. See you then. Bye bye.
ओके अल्लाह हाफिज.
Allah Hafiz.